Hi, good morning everyone.
Morning.
I hope you had a good rest, and it's my pleasure to really introduce Associate Professor Alex Fornito and Dr. Andrew Zaleski from Australia, who will be teaching us about analyzing brain connectivity matrices today. So without further ado, let's begin our class.
Thanks, Eric, and thanks for the invitation. Hello, everyone. So this is something that's new for us, and so hopefully it runs smoothly. But please feel free to tell us if it's not. I guess we've tried to put together something in 2 days. Obviously, you can't teach everything, but hopefully we'll cover the basics, and it will be enough to kind of get familiar with some of the kind of basic fundamental concepts, some of the practical issues, some of the things to consider. And that'll be kind of enough to get you on the road to starting with your own analyses, allowing you to consult the published literature and kind of follow it to however far you would like to go. So I guess we're kind of assuming that people are coming from very different backgrounds with different levels of exposure to either something like MATLAB or something like neuroimaging. And so I guess some of you might find everything really easy, some of you might find everything really hard, some of you might find some things easy, some things hard. But, whatever stage you're at, as we go through, don't be afraid to put your hands up and ask for questions, and then we'll come and help you. So I guess everything's a bit back to front. We're doing a course on analysis before you're going to do all the stuff about image processing and how to generate the networks. But I guess just keep this in mind, and then the stuff that will happen throughout the next week and a bit will be about how you get to where we're going to start. Without further ado, we can get started on today's topic. And so that's basically an introduction to brain network analysis. And so these are the things that I'm going to cover today. So why graphs? Why would we think about graphs? Why would we use graphs to model brain networks? And so I'll talk a bit about the history of how graphs have been used in brain network analysis, and try and give you some motivations as to why you might think about using graph analysis. How do we go about building a graph-based model of the brain? So that involves how we define our nodes, our edges, basic aspects of connectivity matrix, and then basic aspects of analysis. So this is going to be a very introductory lecture, just focusing on the basic issues, so just trying to make sure that we're all on the same page as we get into the more advanced topics. And again, if you've got any questions, just put up your hand. So why graphs? Well, it's often said that the two fundamental principles of brain function are functional segregation and integration. So the idea is that with functional segregation, different parts of the brain are specialized for performing particular functions. And this is an idea that traces back, at least in its modern form, to Franz Joseph Gall, working in the 1700s. His idea was that the size of a brain region was related to how important or prominent a particular ability or trait was in a person's personality. So he went around and measured all the dents and protrusions on people's skulls from all walks of life, and tried to build up a map like this. So he's got traits such as destructiveness just over the ear, language under the eye, he's got memory in the forehead, and so on. And so we now kind of view this as pseudoscience, but that basic idea that different parts of the brain do different things has really been a powerful organising force in neuroscience since then, and certainly supported by famous case studies. So we've got Broca's studies of the patient called the Vaughan, or TAN. So Broca noticed that this patient had quite severe deficits in language production, and after the patient died, Broca had a look at his brain and found that there was quite a large lesion in the left inferior frontal gyrus. We now call this area Broca's area, because he reasoned that this part of the brain must be involved in speech production. Scoville and Milner's studies of HM, so this was a patient with intractable epilepsy who had both of his hippocampi resected, and afterwards he developed a profound amnesia, was unable to lay down any new memories. So then we concluded, well, hippocampus must play an important role in memory. And Harlow's descriptions of Phineas Gage, who used to be a mild-mannered railroad worker, until one day an explosion sent this steel rod coursing up through his skull and piercing his frontal lobes, and afterwards he became quite disinhibited, inappropriate, and quite odd. And so then people started to think, okay, well maybe the prefrontal cortex plays an important role in behavioural regulation. And so from this type of work, as well as electrophysiological work, so we've got kind of the pioneering studies of Penfield, where he mapped the motor homunculus of the brain, showing that there's quite an extraordinary degree of functional specialization in the motor strip. So if you stimulate different parts of this area of the cortex, you can elicit movements in these different body parts. And Hubel and Weasel's Nobel Prize-winning work showing that there's individual cells in the visual cortex that respond to very specific visual properties, such as the direction of a line, or its direction of the orientation of a line, or the direction of its motion. And so, collating all of these results, by the middle of last century, we had a map that looked something like this. So the terms have become a little bit more sophisticated, the mapping is a little bit more precise, but that basic idea is very similar to Gall's initial map. And nowadays, with tools such as fMRI, we can do this with increasing precision and sophistication. Just a couple of years ago, there was an article published in Nature that mapped the specific parts of the brain involved in processing individual words during natural speech. Right, so we can really generate quite precise focal maps of how different parts of the brain are involved in different functions. But we know that this specialization and segregation of function is only part of the story. And we know that from a basic consideration of anatomy. So here we've got two neurons reconstructed with electron microscopy. Then we've got this small section of tissue here that's been reconstructed in full. So the authors have gone through and pulled apart all the different types of tissue. So you can see that there's dendrites, spiny dendrites. So if you go and you map all the different types of tissue that are in this small volume, you find that 92% of it is occupied by axons and dendrites. So this is the tissue that the brain uses to communicate between neurons. This is the connectivity of the brain. So that's telling us such a large fraction of neural real estate is devoted to connectivity and communication. So although specialization and segregation is quite important, well, communication and integration must also be important as well. And really, compared to our understanding of specialization and segregation, our understanding of integrated processes has lagged quite far behind. So it was really in 1991 that Dan Fellman and Van Essen tried to publish the first comprehensive wiring diagram of the neural system in this map of the macaque visual system. So they collated the results of a large number of track tracing studies in the macaque, starting with the retina, moving to the geniculate, and all the higher order areas of visual system. So a couple of years later, Francis Crick of DNA fame and Edward Jones, a famous neuroanatomist, kind of bemoaned the fact that we had no comparable data in the human. We just had no way of measuring brain activity in this kind of sense. And they said this is such an important fundamental aspect of brain function, and we just can't access it at all in humans. It was kind of an auspicious time for them to be writing it, because a year earlier we had the discovery of the bold contrast by Sergei Ogawa and colleagues. And actually in this Nature article they note that, well, there's this new technique called bold, and this might be something interesting. And a few years later, I mean, diffusion MRI had been around since the 80s, but it was really till the late 90s that we saw the development of diffusion tractography that allowed us for the first time to try and chart out white matter connections in the brain. So by the time we got to the new millennium, we started to begin to develop a toolkit to really gain some insight into how different parts of the brain communicate with each other and connect with each other. And so 2005, Lowell Sporns, Giulio Tononi and Rolf Kotter called for a map of the human connectome. So they defined the connectome as a comprehensive structural description of the network of elements and connections forming the human brain. So the emphasis here is on structural. So really what we're talking about is a wiring diagram. The term has since been used to refer to functional connectivity. Technically, it should only be structural. If you think about an ohm is a comprehensive map, so we can do that for structure because structure is relatively stable, whereas functional dynamics are quite transient and variable, so you could have a debate about whether you could actually ever derive an ohm, but that's a bit of a semantic issue. But the idea is that we can generate a connectome at lots of different scales because the brain shows non-trivial organisation all the way from the nanoscale, so we're talking about nanometers, so we've got networks of proteins and molecules that drive synaptic signaling, through to the microscale, where we've got networks of individual neurons and synapses, to the mesoscale, where we've got populations of neurons linked by axonal fibres, and the macroscale, where we've got large brain regions interconnected by white matter bundles. And in each of these cases, we can describe the system as a network. And so then you would think, well, there's all these scientists working on all these different levels, using all these different techniques. Wouldn't it be nice to have a single unifying framework that would allow us to move between these levels seamlessly and to generate some kind of comprehensive understanding of this multi-scale architecture? It turns out that graphs provide us with this unifying framework. And they can do that because graphs are remarkably simple abstractions of a complex system. Because really what we're doing is we're boiling down a system to its essential elements, and that's nodes and edges. So the nodes represent fundamental processing units of the network. So in the brain network you might think of a node as a neuron or a population of neurons. And the edges represent the interactions between the nodes. So whether it's a synapse or some form of functional communication. And so by doing this, we can represent any system of interacting elements as a network, whether it's neurons and synapses or large-scale brain regions and the white matter bundles. So this kind of gives us a common language to begin to piece together all these disparate areas of neuroscience into a coherent whole. Now I'll just talk a little bit about graph theory and how it evolved. Graph theory is really trying to understand the properties of graphs from a mathematical perspective. So once we've acquired our brain data and we reduce it down to a graph, it's a very simple object, and there's very well established mathematical tools that allow us to characterize different properties. And this is the field of graph theory. So the beginning or the origins of graph theory are really credited to this man here, Leonhard Euler, who was really perhaps one of the most prolific mathematicians of all time, made a lot of fundamental discoveries in lots of different areas. But he was working on a problem called the Seven Bridges of Königsberg. So Königsberg is a town in modern-day Russia now called Kaliningrad, and it comprises these different land masses connected by 7 bridges. And the question was, is it possible to find a path that crosses each bridge once and only once without ever doubling back? And Euler was able to solve this problem by representing the system as a graph, right? So he boiled the system down to its essential elements. The land masses were nodes, and the edges between them were bridges. And so you can see he's gotten rid of all of this extraneous detail. We don't care about all the hills and the bumps and the locations of the roads. We just want to know about the land masses and how they interact with bridges. And from that, he was able to deduce that no such path was possible. Now, after that, graphs were used in some niche contexts, some applications in chemistry and so on. But the next big breakthrough came in the 1950s, again on the back of work by another very prolific mathematician, Paul Erdos, who teamed up with Alfred Renyi, and they studied the properties of probabilistic random graphs. So these are graphs where the edges are drawn completely at random with some probability, and they were able to derive a number of analytic expressions that would predict the properties, some properties of these graphs as you varied their size or their probability of connection. And so then this kind of opened up a new way of modeling and thinking about networks. And And so a lot of people since then, after that time, whenever they were confronted with trying to understand a particular network, they would use this random graph model. It's okay, we've got a network of a particular size, we draw the edges at random, let's look at the properties. But it wasn't really until the end of the 1990s where people started to say, hold on, maybe this random graph model isn't entirely appropriate. There's really two seminal studies. One was by Alan Laszlo Barabasi and Rika Albert, published in Science, where they said, well, random graphs, if we just generate a random graph and we look at its degree distribution. So degree is just the number of connections attached to a node, right? And so if we look at that value for all the different nodes, we get a distribution across all nodes, and so the degree distribution is like this. And so if we look at the degree distribution of a random graph, it looks kind of bell-shaped, right? It's kind of Gaussian, and technically it's called a binomial distribution. So most nodes have some average level of degree, and then you've got a very low chance of finding nodes that have got very high or low degree, right? So because everything's generated at random, most nodes are going to have a similar level of connectivity. And they said, well, is that really consistent with real-world networks? If you think about the network of the air transportation network, so flights between different airports around the world, it's not that every airport services more or less the same number of flights. We've got some major hubs, airports like London Heathrow, Kuala Lumpur, Dubai, Singapore, Bangkok, and so on. These airports service a much larger number of flights than a lot of other more local airports. Right? So it seems unlikely that this distribution would be an accurate description of that particular network. And so what they found was that a lot of real-world networks actually have a distribution that looks something like this. So most nodes have got very few connections, but then you've got this extended tail here. And out here you've got these hub nodes, these nodes that have got a very large number of connections. And these are the hubs of the network. Right? And so more formally, they found that this distribution follows what's called a power law, and it's characteristic of scale-free systems. This is something that Andrew will talk about in the next lecture. But the main point to keep in mind at this stage is that what they found was that many real-world networks have got hubs, right? So there's a heterogeneity in the way that connections are distributed across nodes in the network. The other key finding came from Duncan Watts and Stephen Strogatz, where they took a bit of a different approach. They said, well, let's consider two possible extremes of how a network could be organized. On the one side, we've got a random organization. This is similar to what Erdos and Remy studied. And on the other end, we've got a completely regular and predictable organization. So here, each node is connected to its four nearest neighbors. Right? They said, well, what happens if we start with this regular network and we just randomly rewire the edges? And we do this more and more times until we end up with this random configuration here. What happens to the network? They looked at two properties in particular. So one was called the clustering coefficient. Basically, that just involves counting the number of closed triangles. So you can see here in red, we've got a closed triangle here, whereas here between these three, we've got an open triangle. And so you can think of a network, if there's lots of closed triangles, then the connectivity in that network is said to be cliquish, right? You've got these densely connected subgroups of nodes. And they thought that this was a property that captured what intuition would tell you is characteristic of social networks. So in a social network, if I hang out with Bob and Jane, chances are Bob and Jane are going to be friends with each other because maybe we go to the same parties, maybe we like the same things. So there's a higher chance that they're going to be friends with each other than you would expect at random. Right? And so that suggests that a completely random model is not an appropriate model of social networks. So social networks tend to be quite clustered. And they thought, well, this clustering coefficient, this measure of what's the likelihood of finding closed triangles, captures this property. What it takes to get from one node to any other node in the network. So say I start at this node here, I need to go through 1, 2, 3, 4 edges to get to this node here. Right? So we do this for every pair of nodes in the network, and we take the average. And the idea is that a network with a short average path length enables efficient communication. I can get from one point to any other point in the network very quickly. And in general, random networks have got a low average path length because you've just got all these connections going everywhere, so you can get 20-point network with a short number of hops. Whereas a regular network has high clustering, right? All the neighbors are connected with each other, but the path length is quite long. So if I want to go from this point in the network to this point in the network, I need to go through all of these intermediary steps to do so. Whereas in the random network, I can do that in 1 or 2 hops. So they said, well, let's look at these properties, clustering and path length, as we rewire the edges of this regular graph until we get to a random configuration. And they found that at a certain point, you just need to rewire a few edges where you see a dramatic drop in path length, but the clustering remains high. Right, so you're kind of getting the best of both worlds. You're getting high clustering, so you're getting this locally cliquish activity, and you're getting low average path length. So you can get from one point in the network to any other quite quickly. And so they call these networks small world, in analogy to what is commonly said about social networks. So social networks are clustered, yet if you think about the sort of 6 degrees of separation rule, it implies that you could find someone anywhere in the world by just a short number of links if you knew where to go. And they went on to show that lots of networks found in nature showed this small world combination of high clustering and low average path length, suggesting it was a ubiquitous property of nature. One of the networks they actually looked at was the nervous system of C. elegans. And they showed the C. elegans a small world. And so then this obviously provided an attractive way of thinking about the brain, because you could think, well, clustering might provide a substrate for segregation. You've got these local densely connected subgroups of nodes. And low average path length would provide a substrate for integration. Right? You can get from one point to any other point in that way. You know, the picture is a little bit more subtle than that, as we'll see, but that was the initial thinking at the time. Now, another key property that was discovered about many real-world networks is that they're modular. So this is extending the idea of clustering more than just sets of 3 nodes. The idea is that many real-world networks can be decomposed into subsets of nodes that are more strongly connected with each other than with other parts of the network. Right, so you can see here this network, there's 3 broad groups here. Right, they're all densely connected within each other and sparsely connected between modules. And then within each module, we can also decompose it into sub-modules, right? Again, that are more densely connected with each other than with other parts. So we end up with a hierarchical organization, as you might typically characterize as something like hierarchical clustering, and is represented in the dendrogram. So you've got like some high-level organization that splits into 3 groups, and then each of those groups can be split into subgroups and subgroups and so on. And so many real-world networks show this property, including the brain. So then these discoveries and a few others led to the idea that, well, many real-world networks are neither regular nor random, and so then they're said to have what's called a complex topology. Right? It's neither completely random nor completely regular. It's somewhere in between, and this is what we consider to be a complex network. And so then this really gave birth to the discipline or the science of complex networks. And obviously, these realizations coincided with the increasing availability of large-scale network data sets. You could think of networks of Facebook users, Twitter users, maps of the internet, and so on. So now we're starting to collect all these different types of network data. We can analyze the properties and start to get new insights into how things interact with each other. And this is just an example of some of the different types of networks that you could use these tools to analyze. So we could map networks of interactions between proteins within the cell. We can map social networks, such as how different scientists collaborate with each other around the world. We could map the World Wide Web, where each page is a node and links between pages or the edges. We can map transportation networks, so we've got cities linked by roads, and so on. Right. So really the beauty of graph theory and network science is that it is so general that it can be applied to any system of interacting elements. And then it allows us to couch the brain within this broader science of complex systems and complex networks. It allows us to draw on these principles for understanding brain organization and function. So, that's my brief motivation for why you would want to use graph theory and network science to understand the brain. Hopefully I've convinced you. So assuming that we're convinced that this is the best way to think about the brain, say that tongue-in-cheek, we then want to go about building a connectome or a graph-based model of the brain. And so there's a few steps here. Basically what we're talking about is how do we define our nodes, how do we define our edges. So I'll begin by talking about how we define our nodes. Right, so if you think about a brain network, well, a simple answer is, well, each neuron should be an individual node and edges should be the synapses that connect them. And there are people doing this kind of work, but really with the numbers we're talking about, where the human brain contains about 86 billion neurons and trillions of connections, it's unlikely that we'll ever get a map, that resolution of the human brain in our lifetimes. Although people are doing this in model organisms. So then what do we do next? Well, the brain is organised at the level of neurons and synapses, but then it also shows non-trivial organisation at other scales. We can think about cortical columns, we could think about larger populations of neurons, we can think about cytoarchitectonic areas. Each of those scales gives us some kind of meaningful information. So we don't need to necessarily be restricted by the finest grain of resolution. But then as we move up in these scales, the way we define our nodes becomes a little bit more ambiguous, especially when we're dealing with brain imaging data where we don't have access to microscopic features. The question is, where do we draw the boundaries? We know that sulcal and gyral landmarks aren't great borders for different functionally relevant regions. So there's been lots of different ways that have been developed to try and define nodes. I'm not going to try and vouch for any particular method, but in general, some of the ideal characteristics of nodes are that they should be intrinsically consistent. And so that means, for example, if we've got brain imaging data and we're going to cluster a group of voxels into a single brain region, then those voxels should be functionally similar, right? They should represent some kind of functionally homogeneous entity of the brain. The second criterion is that they should be extrinsically distinct. So if I define a node here, then it should be functionally distinct from the node next to it. We should be able to draw functional boundaries between those. And the third is that they should be spatially constrained. Right? So an idea of functional localization or specialization of the brain is that a specialized patch of the brain is an anatomically contiguous area. So we generally don't want a node to comprise brain regions that are distributed in different anatomical locations. So that said, some of the different ways of defining nodes, so obviously the classic, sometimes thought of as gold standard, is cytoarchitecture. It was developed by Brodmann, although lots of other people have developed their own schemes, so one could argue whether it really is a gold standard. But it has been ported into stereotactic space for use with MRI by the work of Simon Eichhoff and Carl Zillies and colleagues, but it currently only covers a relatively small expanse of the brain. We could define regions based on variations in chemoarchitecture, so looking at differences in the distribution of different receptor types. We can use anatomical landmarks, so sulcal and gyral boundaries. This is quite common, but as I mentioned, they don't normally coincide with cytoarchitectonic or functional borders. We could just parcellate the brain at random, trying to ensure that the nodes are equal size. We could use some a priori information, so we could pick peaks from, say, an activation task and generate regions of interest around that. There's a lot of interest recently in data-driven approaches, so using various sophisticated clustering algorithms to try to define boundaries based on similarities in functional connectivity profiles and so on. We could just treat each voxel as a distinct node. More recently, people have started to use variations in myelo-architecture, and last year the Human Connectome project team published their parcellation of the human brain using a multimodal approach that combined information from task data, myelo-architecture, resting state fMRI, and so on. So there's lots of different approaches. My own personal view is I don't think that there's any one single correct approach. typically it's going to depend on your questions and your hypotheses, but it is important to be mindful of the limitations and the pros and cons of the method that you use. So just to kind of talk about those a little bit. So this is a nice illustration of the fundamental problem from Gagan-Week and Steve Peterson's group. So imagine we have a map of the world, right? These are all the natural borders, these are the borders between the countries. But say we don't have that information, how should we parcellate the world? Well, one way would be to use all the boundaries between water and land. So really what we end up doing here is mapping continents. And this is similar to parcellating the brain based on sulcal and gyral landmarks, right? But you can see that obviously we're losing a lot of the finer detail. Like all of Africa is treated as a single node, all of Eurasia is treated as a single node. So then we could say, okay, well, let's just parcellate the map at random. And so this is what we end up with if we zoom in on Europe. But again, you can see that these random borders don't necessarily coincide with the actual borders of the country. So we're going to get a mixing of heterogeneous signals within our node. Or we could say, well, let's just impose a grid on the map. And this is similar to treating each voxel as a node. And again, you can see that it doesn't really correspond to the boundaries of the actual countries. So, the way in which we parcellate the brain will have an impact on the way we're sampling the network, which could potentially affect our results. And certainly this was a nice comparison of different kind of popular parcellation templates that are available in the literature, and they actually mapped the homogeneity within each node. So the homogeneity of the fMRI signal, of the voxels contained within each node in each of these parcellations. You can see there's quite a lot of heterogeneity. So for the AAL, the Automated Anatomical Atlas, which is perhaps historically the most popular technique, it's got quite low homogeneity. And as you kind of use more sophisticated data-driven approaches, you start to get much higher homogeneity. So this is kind of going back to that first criterion of what a good node should be. It should be intrinsically homogeneous. So this is kind of, at face level, it's an important consideration. In practice, it depends on what you're trying to do and what you're trying to say about a brain network. If you've got very specific anatomical hypotheses, then yes, this matters. If you're looking at fairly global properties, then these tend to be present regardless of what you do. So this is a study run by Andrew a few years ago where we parcellated the brain at 82 nodes and then all the way up into 4,000 nodes using random parcellations. And so this is the value of a particular network measure called small worldness. We'll talk about it tomorrow. You can see that the values change quite a lot, going from the coarsest parcellation to the finest parcellations. They go from less than 10 to over 50. But the basic conclusion, is the network small world or not, remains the same. So it depends on the type of inference and the level of conclusions that you want to draw from your analysis. But parcellation does have an effect. So this is using a similar approach in fMRI where you just look at different scales from 84 nodes to over 4,000 nodes. This is computing the correlation between every pair of parcellations on the clustering coefficient. You can see if we threshold the network so there's only 10% of connections, we actually start to see negative correlations between these parcellations. This is in the same data, which is parcellated at different scales. You can get very different results. Whereas if you have more edges in there, it's all moderately positively correlated. So there is certainly an important factor in the way you construct your networks, that this can affect the results and the measures that you get. And so you do need to think carefully about, well, what is it that I want to say about my network? What is it that I'm trying to say? What parcellation is the best suited to my particular question? And usually it's good practice to try and cross-validate your results with different parcellations to make sure that your results aren't driven by the idiosyncrasies of the template you used. So in general, you want to say, are my node definitions valid for the problem that I'm investigating? To what extent do my findings depend on that particular type of parcellation or the particular scale that I've used? So this is where cross-validation with other parcellations can be useful. And another important thing is, can variations in node size account for the findings? So some parcellations, you can have some regions that are bigger than others. And this can introduce bias into the analysis. So this is just a slide in the mouse connectome. So this is track tracing data using an anatomical parcellation of the mouse brain where the regions can vary quite a lot in their size. And this is correlating regional volume with some basic properties such as degree, betweenness, clustering. You can see the correlations can be quite high, so as high as 0.86. So this means that if you're looking at a particular measure across nodes, you can't really be sure whether that variation is just driven by the fact that some regions are bigger than others. So you need to kind of consider this and factor this into your analysis as well. Now, final thing is the problem of individual variability. Historically, people have defined a parcellation on some group average brain, and then we put that onto each individual brain and assume that brain organisation is the same for all people. But you can see this is just a slide from Katrin Amundsen and Carl Zielis showing variability in the location and size of areas V1 and V2 defined using cytoarchitectonics. So you can see that there's quite a lot of variation in the size and the precise location of these areas, right, from individual to individual. So if you use a one-size-fits-all approach, you're going to miss this variability. And so one of the key breakthroughs of the Human Connectome Project approach last year was that their approach does develop individually tailored parcellations that can then be registered to each other. And so this is likely to improve precision and specificity as we move forward into the future. Right, so that's defining nodes. Were there any questions about that at all? Okay. So we'll talk about defining edges now. And in the brain, there are three different types. When we talk about edges, we're talking about connectivity, right? So how brain regions connected with each other. And so in the brain, there are broadly three classes of connectivity. So there's structural connectivity, which is the physical or the anatomical connections between brain regions, so synapses, white matter pathways. And this is intrinsically directed. So each neuron, each axon has a source, originates from a neuron, and then it has a target. Right? So there's directionality there. But with MRI, we can't resolve that directionality. We just don't have access to that resolution. So that's a limitation of our current approaches. Then there's functional connectivity. So functional connectivity is a statistical dependence between physiological signals that we acquire from different nodes, brain regions, and neurons, or whatever. So this is estimated at the level of the signals. So for example, if we're doing fMRI, we take our fold time series, we correlate them. That's a measure of functional connectivity. Correlation is a measure of statistical dependence. We could use mutual information. We could use coherence. They're all just statistical measures of coupling. So they're all under the broad class of functional connectivity. And this could be directed or undirected. And I'll come back to this in a minute. Then finally, there's effective connectivity. And so effective connectivity is the influence that one neural system exerts over another. So here we're really talking about causal interaction, so it's directed, right? Region A causes variations in the activity of region B. And this is described at the neuronal level. And so this is the critical distinction between effective connectivity and directed functional connectivity. So this criterion that effective connectivity is described at the neuronal level means that if our measure for recording brain activity is indirect, such as cold fMRI, then we need some kind of model that maps that signal onto the underlying neural dynamics that generated them. So, I guess a popular technique for doing this is dynamic causal modeling. So dynamic causal modeling has a model of how the bald signal is generated by neural dynamics, and so we specify different models of the causal structure of neuronal interactions. We put it through what's called an observer function, which is the mapping between the neural dynamics and the bald signal, and we see which neural model best explains the bald signal. If we just take bald signals and look at directed functional connectivity, say for example something like Granger causality, then that would more accurately be described as falling under the class of directed functional connectivity.
Can I ask you a question? Can you back up a little bit on the matrix showing the number of parcellation, and then how do you get the negative correlation?
Yep.
And what does that mean? And how does the number of parcellation actually affects the correlation matrix. I guess I'm trying to understand.
So why do you get negative correlation?
Yes, and what does that mean?
So it's, it depends on the interaction between the scale and the density of the network. So as you go to higher resolutions, you get smaller and smaller nodes. And if the network is sufficiently sparse, you could end up with some people where they end up with lots of open triangles. So this correlation is across people, the clustering coefficient across people. So some people might end up with lots of open triangles where previously at a different resolution where a lot of those nodes were in one node, they end up with closed triangles. So I guess the point of that slide is more that there isn't necessarily a direct correspondence between analyses at different scales within the same individual. So if you've got a very sparse network and you're looking
Sparse
at
meaning like a bottom.
very few edges, you start to get the network starts to fragment, and then it kind of starts to lead to somewhat strange results. And we're going to cover the problem of fragmentation later today.
And if the magnetic is direct, can I say it's effective?
Sorry,
If the function of connective is direct, can I say it is effective?
yes, I mean, there's a bit of debate about this. I think it's useful to be quite clear and specific. So, my take on it is that effective connectivity is specifically defined at the level of neural interactions. So, if you were looking at, say, something like Granger causality between maybe local field potentials or spike trains, then maybe you could say, well, we're looking at effective connectivity. But even then, effective connectivity in its initial definition has a much more precise meaning as the minimum circuit model that could explain the observed signal correlations. If your measure of brain activity is indirect, like BOLD or EEG, there are many steps between the neural dynamics that are causing those signals and the actual signal that you're recording. And so then if you start saying, well, A causes B, you can never really be sure. So for example, with BOLD fMRI, two regions might have differences in hemodynamic lag, and that will change the temporal relationship between them, and that would then change the directionality. And so, my personal view is that it's useful to retain that distinction where you have, if you say directed functional connectivity, then well, this is something that's been estimated at the level of the measured signals. Whereas if you say that you've looked at effective connectivity, that means you've proposed some model of the underlying neural activity that generated your measured signals.
It depends on the method you use. If you compare the carrier, you will see it is effective. If you use the method, it's just calculating the direct, at this time it will not be effective.
Yeah, so I guess what I'm saying is that you might have a method that has direction, so Granger causality, say, but if you're just applying that to an EEG signal or an fMRI signal, I think you have to be cautious about saying it's effective connectivity. Because effective connectivity, in its most specific sense, is really about neuronal activity, not what's happening at the level of a signal, right? So if you think about effective connectivity is happening between individual neurons or populations of neurons, and then we're recording things, at the level of hemodynamics or electromagnetic signals. That mapping is imprecise, right? And so if we're only trying to infer directionality at the level of the measured signals, then it's very hard. It can be difficult to be confident that those directions are going to be correct for the neural populations. that we've recorded for.
You mean the effective connectivity rarely used in neural, but the functional connectivity can have a higher level, but the nodes and
I think what I'm saying, if you're recording from neurons, so calcium imaging, spike trains, then you could be more confident in saying, this is effective connectivity. Whereas if you've got a very indirect measure of brain activity, like EEG, fMRI, then I think it's safer to say this is directed functional connectivity rather than effective connectivity.
Between connections of between two nodes, it can be a stimulatory versus inhibitory connections. Is there any way of representation of this, whether there's a positive influence versus negative influence?
And so the question was that in the brain you can have inhibitory and excitatory influences, so is there a way of representing this? There is. So we'll talk about some of the tools with some analyses. Really what we're talking about is dealing with signed graphs, where we have negative and positive edge weights. And that's been developed to different extents depending on the type of analysis, but certainly there is capacity for doing it, but it is very context specific, so it does depend on the specific application, the meaning you assign to the positive and negative edge weights. But especially when we talk about modularity, we'll talk a little bit about that. I'm sorry, I can't hear you.
This slide shows the three definition of connectivity of the network. If I want to make a connection between the sparsity of the network, is it like to which definition? I mean, sparsity in the network that actually affect the system and artificial network make the system efficient somehow. If I want to make this network to a real one that I see here, what is the relation between the sparsity and the connectivity and these three connectivity that we see here?
So what is the relationship between the sparsity of a network and these three connectivity images? So I guess it very much depends on how you measure it. So if, for example, we measure functional connectivity with correlations, then the values of the edges can be anything between 1 and -1, and it's continuously varying, right? So then the sparsity is very much up to you, and you're setting, it's a statistical issue. How do you set the threshold? And Andrew's going to talk in more detail about that. Some methods have an intrinsic sparsity. So for example, if I map structural connectivity with deterministic tractography, I usually won't be able to map tracks between every pair of regions. So that will have an intrinsic sparsity imposed on it. And also in effective connectivity, usually the idea is to try and develop the best model of causal interactions, and that will have some sparsity on it as well. So it depends on how you measure connectivity. So these three definitions are, in a kind of general sense, ways of thinking about connectivity, but then there's the issue of how we measure it. And I'm going to talk about that at the level or at the level of your measured signals. So inferences at the level of the signals are functional connectivity. That could be directed or undirected. Inferences at the level of neuronal activity is effective connectivity, and that's always directed.
So in case of like fMRI, what we're doing, so we can actually use the effective writing for fMRI process and provide it, or it's better to use functional connectivity for it.
Well, estimating effective connectivity with
Because we
fMRI.
have to use the GCAP and other like LFPs and all.
So,
Like local free projection and other like signals that we require, like off patch club and all. There we can use effective connectivity directly because we are recording directly from the
yeah.
or nearby areas. But because these are like indirect signals in fMRI, so it's better to use functional connectivity there rather than effective connectivity.
Well, yeah. So this is an open issue. So getting accurate estimates of effective connectivity from something like fMRI is challenging. And so I guess something like dynamic causal modelling is the most widely used, and historically we've only been able to apply that to small subsets of networks, maybe 5 nodes. More recently there's been developments that allow you to apply it to larger graphs, but the accuracy and validity of these methods is still an open question. If you have access to more direct physiological recordings, then you can be more confident. So, and this is the reason why most of the time in fMRI, most people look at functional knowledge. All right, press on. So, just going on about this issue of how direct our recordings are. So, we can measure both structural and functional / effective connectivity in lots of different ways, right? So structural connectivity, we could do electron microscopy and map neurons and synapses. We can do track tracing. We can do genetic labeling with fluorescence imaging. We can use informatics approaches, so collating the results of large numbers of track tracing studies. More recently, there's been some imaging techniques for post-mortem samples, such as polarized light imaging. But of course, with in vivo humans, we're using diffusion-weighted imaging. Looking at brain activity, we can use invasive electrophysiology, so looking at LFPs, spike counts, and so on. We can do calcium imaging. We can use intracranial EEG to record LFPs from the surface of the cortex. We can use MEG or EEG, or we can use fMRI. So this course is mainly focused on MRI, and so I guess what I'll be focusing on is really issues predominantly focused on diffusion MRI and fMRI. Now, a lot of the analytic tools that we'll talk about are much more general. You can apply it to any kind of analysis, any kind of data set, but at least in this case, in terms of how we build networks, we're going to focus on MRI. So we'll start with diffusion MRI. So I guess you'll probably get a bit more of this throughout the course, but I'm going to give you a very quick crash course. Probably some of you are familiar with this, but the basic idea of diffusion MRI is we're measuring how water molecules diffuse in the brain. And so white matter axonal bundles act as barriers to that diffusion, so water is more likely to diffuse in the axis parallel to the fibre rather than perpendicular. Right, so there's this directional component, and so we can map at each voxel the amount and direction of water diffusion, and map, what path is water diffusing throughout the brain, and we can use that to then propagate what are called streamlines, so lines, where in the simplest case we go to each voxel, we say what's the direction of maximum water diffusion. Okay, I'm going to go that way. Now it's going this way, I'm going to go this way. And you propagate these streamlines until you reach some kind of termination criterion. And doing this, we can map white matter pathways in the brain. This is what's known as deterministic tractography. Alternatively, at each voxel, we can see lots of different tracks in lots of different directions. And we build like a spatial probability map of the most likely path that a tract takes. And this provides us, I guess, an estimate of the uncertainty of a tract. And so these are the kind of two major approaches to diffusion tractography, deterministic or probabilistic. And using that, we can do this throughout the whole white matter and generate maps like these, where we try to map the large white matter fibre bundles of the brain. Now, I'm not going to go into the ins and outs. There's lots of different algorithms of for deterministic and probabilistic tractography. The main thing to keep in mind is that there is generally a trade-off between specificity and sensitivity. So, in general, probabilistic methods, in particular those that use fairly complicated models of the diffusion signal, they tend to be quite sensitive, so you're able to reconstruct more tracks, but they lack specificity, so they're prone to false positives. Whereas deterministic techniques, generally they can be quite susceptible to noise and terminate early, and so they can miss a lot of tracks, so they're prone to false negatives. But by the same token, then they're less likely to result in false positives. So there is a real trade-off, and it really depends on where you're going to sit on that curve. And Andrew will talk a little bit more about the implications that has for network analysis. There are some biases in tractography, well known. So one is distal fading. So say, for example, we have this artificial tract here, and we try to reconstruct that using a tractography algorithm. In this case, we use FSL's ProgTrack. We seed it here, and what you can see is we've got lots of connectivity close to the seed region, and then it gradually fades off, and then it doesn't get to the end point, right? So this is because each voxel that you go across presents new opportunities for a course to veer off track. You might encounter voxels with crossing fibers, which is particularly problematic for these algorithms to deal with. So each time you're propagating, you're kind of having a high likelihood of something going wrong, and sometimes the streamline gets terminated early. So reconstructing long tracks is particularly difficult, but we know that in the brain, regions that are further apart in space are less likely to be connected, right? So we know that in the brain, generally long-range connections are rarer. So this is a graph from the mouse brain showing the probability of a connection between two regions as a function of distance. So you can see if you're a short distance away, you're very likely to be connected, and then it drops off very quickly, exponentially, as a function of distance. So there is a real distance bias in the brain, but on top of that, tractography has its own algorithmic bias that can make it difficult to reconstruct long-range fiber tracks. There's a seeding bias, so longer tracks, which kind of counteracts this distal fading. So longer tracks provide more opportunities for seeding, and so sometimes you can get an overestimate of the strength in those longer tracks. There's an issue of whether you seed using surfaces or volumes. So using volume, so in voxel space, you can see that there's lots of partial volume effects when you get deep into the gyri, where the streamlines can't get all the way up to the top of the gyrus, whereas if you use the surface-based approach, you would be able to. So that's something to consider. And there's more generally a bias associated with whether you're seeding from the fundus of a sulcus or the crown of a gyrus. So this is because you've got these U fibers that connect adjacent gyro, so they go across this way. And all of these fibers here that run parallel to the surface, they make it very hard for tractography algorithms to find a path that runs perpendicular into the grey matter, right? Because you're trying to propagate a streamline, and you've got all these fibers going the opposite direction, and the algorithms normally terminate. So you can see here that if you seed up in the crown of the gyrus, near the sulcus, you can only reconstruct this. If you're up in the crown, you can find a white matter pathway that goes right into the white matter, but down at the fundus, the tracks get stuck right there. Right. So these are just some issues to be wary of. Diffusion tractography, it's quite a powerful tool, and those images of white matter tracks look wonderful, but there are a lot of biases and issues that are currently being worked through. Now the other thing is how we estimate connection strength. So typically we create all these streamlines, and then we estimate connection strength as either the number of streamlines that connect two regions, or we measure some aspect of tract integrity. So something like fractional anisotropy, which tells us about how water is diffusing in the brain, and that's an indirect marker of axonal organisation. And they're the sort of two most common ways of estimating connection strength. But there are problems with these. So these are very indirect markers of axonal connectivity. So these streamlines, they're not the same as axons. They're just tracing paths of water diffusion throughout the brain. And these issues are talked about in a lot of detail in this paper by Derek Jones and colleagues, which really goes into all of the biases and problems associated with estimating connectivity using these metrics. So if you're going to do work in this area, this is a paper worth checking out. Now there is hope. There's a lot of active work being done on trying to derive more quantitative estimates of connectivity using different models of the diffusion signal. So people are starting to look at trying to get measures of axon diameter density, myelin content, and so on. But these are quite new techniques, and hopefully will start to proliferate and become more accepted in the next 5 to 10 years. Despite all those limitations, there is a correlation between diffusion MRI connection weights and connection strengths you would estimate using gold standard techniques such as track tracing. So this is data from the macaque. Here we've got connection weights based on track tracing. Here we've got connection weights based on diffusion MRI. You can see that there's a decent correlation there. But you can also see that there's these false positives here where track tracing tells us there's no connection, but tractography is saying we've got some non-zero estimate of connection strength there. Now this is just another study from the macaque, again showing a correlation. These correlations aren't huge, so there's plenty of room for improvement, but despite the limitations, these measures of diffusion MRI are in the ballpark. So that's structural connectivity. Any questions about that?
So can we quote that in structural activity there in using diffusion MRI, like node A and node B are connected, so the connection is like from A to B or B to A. So direct. So what about your comment on the direction?
Yeah, so this is the big limitation of diffusion MRI. We can't resolve directionality.
Because there is always an interpreter between both kind of transmission and neurons. So we can't say that that fluid is flowing from A to B or B to A, and about where is the axonal body and where is the so about the axonal body, where is basically the axon and the cell body basically of a neuron. So is it better to have an estimate from A to B and B to A and then have an average about the total number of count of neurons connecting A and B?
So if you seed from region A and then seed from region B.
Yeah.
I mean, I think that's, so that's not going to give you directionality in the sense of actual axonal fibers.
But also there are the differences when we have a mask on A and mask on B, and if we will have like from A to B, the numbers are different, but if you will go from B to A, the numbers are different. So
yeah, so if you're seeding from grey matter, then that would be one approach. Other approaches are to seed from the white matter volume, where you basically just seed all the tracks from the white matter volume and map which ones intersect two grey matter regions, and then you don't have to do this kind of symmetric approach. Okay. All right, so now we'll talk about functional connectivity. So I'm going to focus mainly on functional connectivity because that's what's typically used in the fMRI literature and typically used in the context of graph analysis. As I mentioned before, effective connectivity, particularly for large-scale networks, is it's still a developing area. So the basic idea with mapping functional connectivity with fMRI is we put people in the scanner, we do some pre-processing, and then we extract time courses of signal fluctuations from our nodes. Right? So we've got all of our different nodes, and we measure how the bulk signal fluctuates in each of those areas. And that's kind of, from then on, we go and build our network. I'm just going to give, you're going to do some exercises later in the week about processing data, and you'll see some of the issues. But I'm just going to talk a little bit about how pre-processing can affect the conclusions you draw from an analysis. So I guess one of the big issues, so there's lots of different pre-processing steps in fMRI. And one of the big ongoing controversies, for example, is how you deal with head motion. And so this slide just illustrates that how you actually try and deal with this problem does have an effect. So here we've got 16 different motion correction pipelines. And what we've got here is, after we've applied that correction, how many edges in the brain, how many connections in the brain show a residual correlation with motion across people. And so you can see if we do the simplest thing where we just take our 6 head motion parameters and regress them across our bold time series, over 50% of the edges are still correlated with motion. Right? So you can still have quite strong contamination. If we do if we do an expansion, so we look at the motion parameters plus squares plus derivatives, which is often recommended, 68% of the edges are still correlated with motion. And then you can use other methods where you can bring that number right down, right? But it is important to think about how your pre-processing pipeline is performing and whether it's doing the job that it should. It has a practical impact on the conclusions we draw. So then if we go and look at a comparison between people with schizophrenia and healthy controls, so here we plot the percentage of edges that show a difference either for schizophrenia greater than patients on the left side or for controls greater than patients, schizophrenia greater than controls on the left, controls greater than patients on the right. You can see, depending on your pipeline, you can end up with very different conclusions. So if I use these pipelines, I think, well, functional connectivity is only increased in patients. If I use these pipelines, I think, well, functional connectivity is only increased in controls. And then if I map that on the brain, this is under one pipeline, I say, well, there's global increases in patients. If I use another pipeline, well, there's global decreases in patients. If I use another pipeline, I say, well, there's a combination of increases and decreases. Right? And this is the same data, it's just different pre-processing strategies. So it's very important to think about the pre-processing strategy and think about quality control metrics and try and be as transparent as possible about the impacts of motion. If anyone's interested, this paper's on bioRxiv and you can have a look at it, and it's got some recommendations about how you might report quality control issues. At this stage, I just want to point out that pre-processing matters. We then want to go and build our network, so we've got our node time series. Then we compute some measure of statistical dependence, so it could be correlation, partial correlation, mutual information, and so on. And we build our network. Now the critical thing with fMRI is there's broadly 3 different ways we can measure connectivity. So one is with a standard resting state analysis. And so in this case, we just record signal fluctuations over time as a person lies in the scanner without performing a task. And this is assumed to be a fairly stable psychological state. And so then we record this for all the signals and we summarize all that activity over that period with a single value, such as a correlation value. So it's kind of, you can think of it as like an average measure of the dynamics over that period. And then we go on and build our networks. More recently, people have become interested in looking at actual dynamics, so trying to look at how this signal varies over time. So in the most common or simplistic way, you could do a sliding window analysis. So you chop this time course up into segments, say of 30 seconds or longer. Those windows could be overlapping or non-overlapping, and then you end up with a series of networks. And then you can look at how the network evolves through time. And it's important to do appropriate statistical controls for this, and this is quite a contentious issue in the field at the moment. Then the other option is to look at brain activity during a task. In this case, it's a little bit more complicated because the task is driving activity in a particular way. So if we just take our bold signals and correlate them, we're not really going to understand whether a correlation is driven by what's happening during the task or some intrinsic background spontaneous property of dynamics. And so typically we want to use a method or a model that allows us to isolate the task-dependent component of network connectivity as distinct from background intrinsic fluctuations. And so I'm not going to go into the details of that, but there are some references there for those people who are interested. It's just important to think that depending on what exactly we want to look at, we need to tailor our analysis. Now, the measure that we use to estimate functional connectivity also has an impact on network analysis. And most commonly, functional connectivity is estimated with a simple Pearson correlation. And this measure has known biases that can affect your network analysis. So, say we've got a pattern of structural connectivity that looks like this, right? B connects to A and C, but A and C are not connected. Generally what will happen if we use Pearson correlation is we'll find some correlation between A and C. Because A correlates with B, B correlates with C, so that mathematically B and C need to correlate with each other as well. Right? So correlations have this property where they tend to close triangles. And so you end up with networks that are more clustered than random. Right? In the case of a closed structural triangle, it's not a problem, it'll be reasonably accurate. In the case of an open structural triangle, you get this triangle closure effect. So then, if we look at clustering and we compare it to completely random graphs, right? So sorry, with this analysis, we started with just completely random signals, so just random numbers, and we correlate them, and then we measure the properties of those networks. So in this case, we've got clustering, and then we compare it to a network where we've completely drawn the edges at random, so we know it has a random topology. And so then values greater than 1 mean that our random correlation network actually has greater clustering than it should have. And so you can see, as a function of threshold, we get higher clustering. So these correlation networks are more clustered than they should be. That's simply a bias introduced by the fact that we've used the correlation and it's got this triangle closure effect. So you might say, okay, well, we should use partial correlations instead. And in that case, in the case of an open triangle, partial correlation will probably do a good job, and we'll just find the direct interaction between A and B, direct between C and B, and probably find nothing between A and C. But if there's a closed triangle, it becomes a little bit more ambiguous as to what the partial correlation does, and this depends on things such as the number of nodes in the network and the covariance structure. What we actually found in this experiment was that partial correlations lead to networks that are less clustered than they should be. So it over-penalizes in the context of large-scale networks. Now, there are techniques that allow you to perhaps find some kind of happy ground in between these. These are called penalized inverse covariance. So you have a regularization parameter that constrains the partial correlation estimation. And these might help. So you can check those out, but this is just to point out that the actual way in which you measure functional connectivity can introduce biases. And so if you're going to use correlation networks, sometimes you need to think about the specific null models that you're going to use as benchmarks to make sure that whatever you're finding is not driven by simply the fact that you've chosen to use a correlation coefficient. So are there any questions about that? Okay. So let's say though, given all those issues, we're happy with the way we've defined our nodes, we're happy with the way we've measured connectivity. The next step is to then build a graph. So we've got our nodes, we've got connectivity between every pair of nodes, either structural or functional, and then we represent that in the form of a connectivity matrix, often called an adjacency matrix. So here each row and column corresponds to a different region, and each element tells us the type and strength of connectivity between every pair of regions. So for example here, element 2, 1, that's the connectivity between region 1 and 2. From that, we can generate a graph representation of the network. And mathematically, these two are equivalent. So even though we talk about graph theory, usually we're doing analyses on matrices. Right? And I'm going to go into that in a little bit more detail. So let's start by focusing on the connectivity matrix. So really the first connectivity matrix for the brain was published in that seminal article by Dan Fellerman and Van Essen in Cerebral Cortex in '91, where they summarised the results of lots of track tracing studies in the macaque. And then we can fast forward and generate more sophisticated visualizations. So here they were just saying, well, is there a connection or not? How certain are we? Here we can get more graded variations of the strength of connectivity. And it all follows the same basic format, right? So here we've got different regions along rows and columns. And so then along the diagonal, we've got the connectivity of each region of itself, right? So 1, 1, 2, 2, 3, 3. And so this is conventionally set to either 1 or 0. And then in the off diagonal, we've got the connectivity between pairs of regions. So for example, here the connectivity between region 1 and region 2 is 0.8, between 1 and 3 is 0.5, 4, 5, and so on. And we can split this matrix into an upper triangle, so everything above the diagonal, and a lower triangle, everything below the diagonal. Right? Now, in the case of an undirected network, so say a diffusion MRI network or a correlation-based network where a measure of connectivity is symmetric, the upper triangle and the lower triangle are the same. They're mirror images of each other. So if I go to element 1, 2 or element 2, 1, I've got the same value, right? because I'm not representing directionality in any way. I'm just saying two regions are connected, but I'm not saying A goes to B or vice versa. So in this case, we can say Aij equals Aj. So the first index tells us the row, the second index tells us the column. In a directed network, that's not the case. And it depends on how we list our connections. You could choose to list outgoing connections along the rows or along the columns, and that means that the upper and lower diagonal of the matrix are going to give us different information. So that depends very much on how we've measured connectivity. We then have to think, well, I've got my connectivity matrix. Do I want to apply some threshold? So most of the time, our measurements have some level of noise. And so then it can be useful to say, well, I'm going to apply a threshold. Everything below this threshold is noise. Everything above, I think, is real. I'm going to focus on that. The threshold can help to emphasize the real actual properties of the network, make sure that noise isn't making a contribution. But there are issues with how we choose that threshold. This is something that Andrew's going to focus on a lot in the next lecture. But we can go from a weighted network to a weighted and thresholded network. And then sometimes also people binarize the network. So they get rid of that weight information and they just say, I'm just going to focus on where connections are. I'm not going to worry about differences in the strength of connectivity. This depends on the types of conclusions or inferences or analyses that we want to make or draw. Now some methods that we use to measure brain connectivity come with their own intrinsic threshold. So if I measure connectivity using a deterministic tractography algorithm, as I said, these are less prone to false positives but are also susceptible to false negatives. And for a given person, I might end up with a network with 28% connection density, so 28% of all possible edges. If I use a probabilistic tractography method, which again, as I said, are more sensitive but also more prone to false positives, then I end up with a network with 60%, which is real. This is the same person. And so this is where thresholding becomes important. And so again, this is a limitation of our measurement techniques. Right? Things like diffusion MRI, fMRI, they're quite noisy, and so then this is where thresholding can become important. Once we have our matrix, we can reorder it in different ways to visualize or emphasize different network properties. So in this particular case, we've got all left hemisphere regions followed by all right hemisphere regions, and it's ordered so that region 1 in the left hemisphere is the same as region 2 in the right. Right? So they're homologous. So then what you can see is there's much denser connectivity within hemisphere than between hemisphere. Right? So a lot sparser. Oops. And then you've got this sort of diagonal elements here along the parallel. This is the main diagonal. You've got these parallel diagonal elements. This is each region connected with itself in the other hemisphere. Right? And so that gives you some idea of the anatomical organization of the network. So, going back to this idea that matrices and graphs are the same. So let's take this toy example here with 6 nodes. So here is the graph, and here is the matrix representation. So basically, I've got a 6 by 6 matrix, and wherever there is an edge between nodes, I put a 1 in the matrix. So we go to row A, column C, I've got a 1 because there's a connection between A and C. We go to row B, column D, I put a 1 because there's a connection between B and D, right? And so on and so forth. And again, this is undirected, so the matrix is symmetric. So AC, I've got a 1, CA, I've got a 1. Okay? We could represent weights. In this case, this is represented by different edge thickness in the graph, and in the matrix we could just use different colors. So you can see here there's a strong edge from C to F, and F to C. So if we go to row C, F, that's the kind of, that's the red color, the strongest color in the matrix. So now we've got a directed graph, a binary directed graph. And so here, the upper and lower triangles are not symmetric, they're not the same. So if we have a look here, I've listed outgoing connections going down the rows. So here we've got a connection running from A to E, but not vice versa. So if I look at row E, column A, I've got a 1. If I look at row A, column E, there's nothing. Right? And so that's how you encode directionality in the matrix. Again, people use different conventions. Some people might list the outgoing connection here. It depends, I've just done it this way. Whereas here we've got a symmetric connection between A and C, right? So A to C and then C to A, so we go to AC1 and then CA1. And then we can do the same with weights. We just look at thickness and colours and so on, right? So that's how graphs and matrices can be, are equivalent. Given all these different types of graphs, what type of graph best represents the brain? Well, we could start with the simplest thing, binary graph. There's nodes connected by edges. This is what a lot of people have done historically. But as we know, different brain regions are connected with different levels of strength. Track tracing tells us over 5 orders of magnitude, so we'd want to incorporate that information in some way, so we could use weighted graph. I also mentioned that each connection has a source and a target, so the network should be directed. And we also know that not all brain regions or nodes are the same, right? So we've got nodes vary in terms of their cytoarchitecture, their neurochemical profile, their intrinsic dynamics, and we might want to represent that heterogeneity in some way. So maybe we need to incorporate node heterogeneity in our representation. And we also know there's different types of connections. There's excitatory, there's inhibitory, there's modulatory, and so on. So really what we're talking about is some kind of hybrid graph. On top of that, nodes are distributed in the brain through space, so we want to account for spatial positions because space has an important role in brain organization. And brain networks evolve dynamically through time on scales ranging from milliseconds to years. So we want to be able to incorporate this. Now, graph theory provides us with a formal framework for incorporating all of these aspects. Right? It is possible, but largely due to, in many cases, the limitations of our measurement techniques, most people have focused on just the simplest case, binary connectivity. And as you get to these more complicated cases, looking at heterogeneous edges and directionality and so on, this is possible with more invasive techniques, so electron microscopy and so on, or perhaps using sophisticated modelling such as DCM to fMRI. But this tends to be relative small subset of papers in the area. Most studies, particularly in human imaging, are using either binary or weighted undirected graphs. So we've got a lot of room to improve as our measurements get better. Graph theory gives us space to grow in terms of how sophisticated our models can get. So I'm going to close by touching briefly on network analysis, which is going to give you a bit of an overview for what's going to happen over the next couple of days. So the pure-type brain graph, then there's 2 broad types of analysis we can do. So one is connectivity. So this is really when we're looking at differences or variations in the strength and type of connections between brain regions. And in a lot of cases, people want to do this on a connectome-wide level. So we've got a network with thousands of edges and we want to map which edges correlate with behavior or different between groups and so on. But this is a very big multiple comparisons problem. So in a directed network, we've got n squared minus n edges. In an undirected network, same number divided by 2, right? Because the equilateral triangle are mirror images. So how can we do that? Say we've got a group of patients and controls, and we want to do a comparison of each of these edges, right? So in this case, there's only 90 odd regions, and there's thousands of different brain regions. So the multiple comparison problem scales with the size of our network. If we've got 10 nodes, 45 independent connections in an undirected network, we need a bond-Ferroni threshold of 0.001 to declare anything significant. If we're dealing with 100 nodes to 1,000 nodes, which is what most studies do, we need sample sizes on the order of a GWAS to be able to find anything significant. So one solution to this approach is to use graph theory to cluster connections into related subnetworks and use that to help our inference. And this is an approach Andrew developed called the network-based statistic, and he's going to do a tutorial on that in the last session. We can do analysis of connectivity at the node level. And so in this case, we're typically collapsing data across a row or a column of the matrix. So in the case of an undirected network, say we want to look at node degree for node C, we just sum all the elements in row C or column C. That tells us the degree is 3, and that's our nodal measure for node C. In a directed network, again, we can look at in degree, so the incoming connections, or out degree, the number of outgoing connections. And we either sum the row or column depending on how connectivity is represented. In weighted networks, we can measure something called node strength, which is the weighted analog of degree, and that's just the sum of the weights. So instead of summing 1, 1, 1, we sum, say, 2, 5, 20, or whatever. Right? That's the same problem. Then in sign networks, such as correlation networks, we've got positive and negative weights. We need to think about, well, what do those mean? If we just take a sum, maybe that's not what we want. Maybe we don't want to sum across negative edges. Maybe we want to consider them separately. So that needs a bit of thought. And then we can map those on the brain. We can say which regions are the most strongly connected, in the macaque or the human. Or we can map differences between group at the level of each node rather than each edge. We do it at each node. And then we've got much smaller multiple comparison problem. And then we can do things globally. So we could just take mean connectivity across the brain, of course, and we compare that. Then the last thing, the other thing we can do is look at topology. And so this is really where we use the mathematics of graph theory, and this is what most of the next 2 days is going to focus on. So let's say I've got a network here. This is my connectivity matrix. I can project the network into anatomical space and look at where all the nodes and edges sit in the brain. But I could also project the network in this space, in which case I'm clustering nodes that are more strongly connected to each other closer together on page, and this is 3D. I could generate something similar in 2D, or I could put them on a sphere and look at all how the connections track across each other. Now, the thing that doesn't change across all of these representations is the topology. Which pairs of regions are connected with each other? These are all very different representations, but the basic profile of how pairs are connected with each other is the same throughout. So, more formally, the topology of a network is any property that's preserved under any continuous spatial transformation. So if I stretch it, I rotate it, I enlarge it, or I shrink it, as long as I'm not cutting it or doing anything like that, the topology is what's preserved, and that's basically just which pairs of regions are connected with each other. And so when we're looking at topology, then we're sort of saying, well, I'm not going to look at space, I'm just really going to look at how connections are arranged with respect to each other. Then we're really talking about, well, what are the underlying organizational principles of the network? And this is where graph theory can be quite powerful. And so there's been a lot of work that's gone into trying to understand, well, what are the key topological properties of the brain? And this is a kind of very coarse summary of all of that work, but the basic idea is that the brain can be divided into subsets of nodes that are called modules. So these modules are strongly interconnected with each other, so we presume that they serve some kind of common function. So you could think of this as some kind of functional subsystem, like the motor system or the visual system. And each of these modules has one or more hubs, so highly connected nodes, and these hubs are strongly interconnected with each other. So they form almost like their own module that sits on top of these other more specialized modules. And this is more formally called the rich club. So it's a subset of hub nodes that are strongly connected with each other. And so these modules are segregated, and so they support functional specialization. And this connectivity between hubs, this rich club, you can see supports integration between these modules. If I want to send a message from this module to this module here, I need to go through this rich club kind of connectivity to do so. So we've got this sort of topological substrate that supports both segregation and integration. And we're going to see how to do these kinds of analyses in the next couple of days. Now the last thing I'm going to close on is briefly touch on null models. So in the last lecture, Andrew's going to do more of a detailed overview of null models, but in order to get through the next couple of sessions, we just need a basic understanding of what they're doing. And so this is basically, null models allow us to say, well, okay, I've measured a property in my network. I've measured property X. Is that important or not? How can I tell? Well, I need a null model to say, well, does my brain express this property more than I would expect by chance? Right? So then it's very common in network analysis to follow this kind of procedure. We measure a given property, X, we then measure it in a null model, and then we generate many null models and many null measurements to get a null distribution. And then we see where our observed property sits on that null distribution. And so typically if more than 95% of the null values are less than our observed value, we declare it as significant. Right? So then it implies that our brain shows this particular property more than we would expect by chance. And the critical thing here is in saying, well, what is an appropriate null model? So as I mentioned before, Udos and Renyi proposed the probabilistic random graph, and that was used quite a lot. But we now know that a lot of brain networks are not really accurately described by this random graph model, and many of them show hubs. And so this degree distribution has a lot of effects on network properties. And so the most common null models we use now tend to match an observed network for the number of nodes and edges, but also the degree distribution. And so the most common procedure for doing that is what's called Maslov and Sneppen rewiring. So Maslov and Sneppen were the authors of this paper in Science. The basic idea is you find two edges. So here this edge connects these two nodes, this edge connects these two nodes, and then you rewire them, right? And so you do this many times throughout the network, and this makes sure that you've got the same number of edges attached to each node, but it randomizes everything else. Right? So this algorithm preserves the number of nodes, edges, and degree distribution. And then that's a commonly used null model in network analysis. And in some of the exercises, you're going to be using this for inference on networks. There are other more sophisticated null models that account for spatial properties, that are useful for weighted networks, directed networks, for correlation-based networks, and so on. But Andrew might go into some of those later tomorrow. So to summarise, hopefully I've convinced you that graphs are useful models of brain networks. There's different ways of defining nodes and edges. Each method has a pro and con, and so we need to be aware of those as we're doing our analysis. We can have directed or undirected, weighted or unweighted networks. We also have room to incorporate further details as our measurements become more sophisticated. And we can look at networks in the level of connectivity or topology, and at the level of individual edges, nodes, or globally. Yeah.